Okay, so I'm really excited about this lesson because almost everything that we've done leading up to this particular moment is leading us to doing statistical tests. So last time we talked about statistical tests and what they were. Today we're going to talk about how to actually run one. We're going to run a statistical test today. So this is the heart of statistics. So what we're going to do today is we're going to learn how to look at some data and decide whether or not that data is true or false. And so what we're going to do is it's actually very, very simple. It's just that it uses a lot of the information that we already have. So what we need to do is we need to calculate a test value. And today we're going to use z-test. Tomorrow we'll use t-test and so forth. So we need to come up with a z-value. You'll have two different z-values. You have the z-value that you find from the chart and the z-value that you calculate from your data. They are two different things. This z-value is your test value. So we're going to call this z-test. All right, so the test value is whatever your mean that you came up with, your sample mean, minus the population mean, divided by the standard deviation over the square root of the sample. Now this should look very, very familiar because you should have had this in when we were doing confidence intervals. So how to run a test, a statistical test. The first thing to do is to state the hypothesis and identify the claim. This is what we learned in section 8 too, so you should already know how to state a hypothesis. Then you need to find your critical value, your z-value from the chart. Then you will compute your test value using this, and then you will make a decision to reject or not to reject the null hypothesis. This is going to be something you have to do. You have to make a decision. All right, what does this mean? All right, if you can reject the null hypothesis, then that means that your data is correct. If you cannot reject the null hypotheses, then your data means nothing. So, this is an interesting. This is about getting into it. And just because you run a test, if you were to do your project and you were to run a test and you could not reject the null hypotheses, does not mean that everything was done in vain. It meant that your hypothesis was wrong, but it's still a sound statistical test. So, example 1. It has been recorded that the average credit card debt for college seniors is $3,262. The state senate at a large university feels that their seniors have a debt much less than this. So they think that their students are better, that they haven't racked up as much debt. So it conducts a study of 50 randomly selected seniors and found that the average debt is $2,995, with a sample standard deviation of $1,100. With alpha equals 0.05, is the student senate correct? So do they really have, so this number, yes, this number is less than that number, but is it statistically significant, all right? Is there really enough difference between the two to say that, that their data is less? So the very first thing that we're going to do is to state our hypotheses. So first of all, the null hypothesis is that their data will be the same or greater than 3262. And the alternative hypothesis, which is what we want, is that our data will be less than 3,262. So our critical value, if you look in your chart, is negative 1.65. It's less than, so we want it to be a negative number, okay? So with alpha equals 0.05. That's how you know. If it's less than, it's going to be negative. If it's greater than, it will be positive. So at alpha equals 0.05, my critical value is negative 1.65. And so if my number is less than that, then I do have, then my data is correct. So our formula is x bar minus mu over the standard deviation divided by the square root of n. So 2,995 minus 3,262 divided by 1,100 over the square root of 50. Check your calculators. Okay. So I end up with a critical value of negative 1.72. Okay, since that number is technically less than negative 1.65, see in my chart, in my picture, it's less than that. It's in what's called the rejection region or the critical region. That means that I can reject my null hypotheses, which means that students at this university have data, or have credit card debt that is statistically significantly different. I want to go back just a moment. That is statistically significantly different than this. Okay, it is statistically significantly less than the average. Okay, so they can make the claim that their students manage their money better than most college students. So, all right, here's your practice problem. A researcher reports that the average salary of assistant professors is more than $42,000. A sample of 32 assistant professors have a mean of $43,260. At alpha equals 0.05, test the claim that the assistant professors earn more than $42,000 a year. The standard deviation of the population is 5,230. So you're going to claim that it's less than. So the first thing you need to do is to state your hypotheses, find your critical value, calculate your test value, and then decide if you're going to reject or not. Okay, and here's the solution. Okay, so the solution says, first of all, that our claim is that the mean will be greater than 42,000. Okay, the critical value is, since alpha is equals 0.05, the critical value is 1.65. Then we calculate the data, okay, 43,260 minus 42,000 over 5,230 divided by the square root of n equals 1.32. Now, since this 1.32 is less than 1.65, it's not in our rejection region, we can't reject the claim. We cannot say that these professors actually make more money than $42,000. Okay? So, example 2. An average salary for public school teachers for a specific year was reported to be $39,385. A random sample of 50 public school teachers in a particular state had a mean of 41,680 and a standard deviation of 5,975. Is there sufficient evidence at alpha equals 0.05 level to conclude that the mean salaries differ from 39,385? Now, usually in a situation like this, you would run a two-tailed test because you already know that this number is bigger than that number. But usually you will develop your hypotheses before you know what this number is. So all they wanted to say was that their public teachers made different than the average public teacher. So they actually created the hypotheses before they found the data. So this will be a two-tailed test. Okay. So our H naught is that it is the same, that the mean is equal to 39,385, and our alternative hypotheses is that the mean is not equal to 39,385. So for a two-tailed test at alpha equals 0.05, our t-value, or our z-value, sorry, we're not at t yet, t's tomorrow. Our t-value, or z-value, is 1.96, okay? This should sound familiar because this is a two-tailed test, which is basically like a confidence interval. It was 1.96, okay? So our z-score is 41,680 minus 39,385. So divided by the standard deviation, 5,975, over the square root of 50. Now we want this to either be greater than 1.96 or less than negative 1.96. And we get 2.72. That's significantly bigger. So we can reject the null hypothesis, and we can say that these salaries are definitely different from each other. Now, here is your practice problem. It says a medical rehabilitation education foundation reports that the average cost of rehabilitation for stroke victims is $24,672. To see if the average cost of rehabilitation is different at a particular hospital, the researcher selects a random sample of 35 stroke victims at the hospital. Now, remember, he determined his hypotheses before he found his data. So he said, I just want to know if they're different. Okay, so he calculates that it's 25,226. The standard deviation is 3251. At alpha equals 0.01, can it be concluded that the average cost of the stroke rehabilitation at a particular hospital is different than that? So go ahead and pause the video, see if you can calculate this on your own, and then continue. Okay. So here is my my solution. So here's our null hypotheses that they're the same, the alternative hypotheses that they're different. Okay, alpha equals 0.01. It's a two-tailed test, so this is my critical values are plus and minus 2.58. I plug all these numbers into the formula, and I get 1.01. This definitely falls not within the critical values, so I cannot reject my hypotheses. I cannot say that the data is different. According to this, the data is pretty close to the same. Okay. And that's it. And I will see you tomorrow.